mean deviation. Now, remember what deviation means? If something deviates, it means it's different from something else. It's different from another score, let's say. Mean deviation. We talked about deviation scores, remember? A deviation score is the distance between x, which is just a score in your distribution, also called a raw score. Okay, a raw score is just a score that you haven't done anything to. So it's the difference between a raw score and the mean of the distribution. That is the most common deviation score. So let's look at these deviation scores and how we can use it to estimate variability. So let's pretend that this is you. X bar is you. And all these X's, these are your friends. And what we're looking at here is the distance that they live from you. So here, this is one of your friends, lives very, very close to you. This one also lives very close to you, etc. All of your 6 friends here live very close to you. You're all kind of clustered or clumped together. There's not a lot of dispersion. There's some, because they don't live in the same building as you. They don't live in the same apartment. So there's some dispersion away from you. But overall, the amount of clustering is pretty small. Now, couldn't we just say, well, let's calculate the average, in other words, the mean distance people are from us? We could certainly do that, right? 1 block away, block and a half away, 2 blocks away. We could calculate the average distance people are from ourselves, okay? And then, you don't have to talk about friends. We can just look at scores, actual numbers, and say, well, on average, how close are these scores to the mean, okay? And we would expect the answer to be pretty small here, right? Because of all the clumping. Now, consider this. Here we see a lot more dispersion, right? Again, here's you, here are all your friends. Now you can see that your friends are a further distance away from you on average, right? So this one might be still a little close, but if we look out here, these friends, maybe these are the ones that live in Parowan, all right? Or maybe St. George, and here's you in Cedar City, okay? So as the numbers begin to spread away from the mean, so these numbers are considerably lower than the mean, these are considerably higher, we see that the average distance to the mean is getting larger, right? Here there's less dispersion. The average distance to the mean is pretty small. Here the average distance that these scores are to the mean is getting much larger. So we would say, yeah, this data set is more variable than this one. This one has more clumping or clustering. It's less variable. This is more variable. The average distance scores are to the mean. These scores are to the mean on average would be much larger. So we're thinking, so far so good, right? Just calculate the average, in other words, the mean distance that scores are to the mean. And that will tell you how variable your data set is, how much dispersion there is. Well, not so fast. There is a huge problem with this. So you know the expression, we're going to throw a monkey wrench into this idea? That's what we're going to do now. If we look at the formula, and here we can just rationally think about what the formula would be. We want the average distance scores are to the mean. So that means we have to calculate every distance x is to x bar. So we're going to go x minus x bar to get the first distance or deviation. Then we do it again, x minus x bar to get the second distance or deviation. And we keep doing it until we've got all the distances. But remember, we want an average, so specifically a mean. So what do we do to calculate the mean distance? Well, we have to add up all of our distances. In other words, add up all your deviation scores, right? And then divide by however many scores you have. And that will give you the average, the mean. And on the surface, it doesn't seem like this should be a problem until you remember one important property of the mean. When we add up all the deviation scores around the mean, what happens? We get 0. Remember, the mean is the center of gravity? So that means that the scores, if you were to do all the x minus x bars below the mean, you would get negative distances. And then when you do all the x minus x bars above the mean, greater than the mean, you get positive distances. And then since the mean balances all those differences or distances, they're going to add up to 0. So it doesn't matter what n is, because 0 divided by n is 0. So no matter what your data set looks like, your mean deviation is always going to equal 0. And that just doesn't make any sense, because you can be looking at your data set going, I know there's variability here. Why am I getting 0? And this is the answer. Okay? We can't do this. But then somebody came along and said, well, so the problem is that the scores are adding up to 0, right? These deviation scores are summing to 0, so we have to make sure that that doesn't happen. So somebody thought they had a brilliant idea. They said, to solve this problem, all you have to do is take the absolute of each deviation score. So you see how this is a deviation score? Do you remember what taking absolute values does? So if, let's say, this number in here, when we did the x minus x bar, if this was negative 3, what would be the absolute value of negative 3? It would be positive 3. So if this is negative 5, the absolute value would be positive 5. What if your number is already positive? Like what if you had 10, positive 10? Well, then the absolute doesn't change it. It stays positive 10. So absolutes only change the negative numbers. They just change them from negative numbers to positive numbers. And that solves the problem, right? Because yes, you're going to have negative numbers up here, but you just pretend, it's kind of like pretending they're all positive. So when you add them all up, you're no longer going to get 0. Problem solved, right? No, because what you've just done is you've created other problems. So you're likely to be frustrated now, saying, just when I thought I had the perfect solution, I find out it's a crappy solution. And here's why. 1, you have just engaged in a form of numerical discrimination. It's like you're telling those negative numbers that they have to change, but positive numbers, they're just fine the way they are. So you see how that's discrimination? It's numerical discrimination, and that creates problems down the road. What problems it creates, I'm not exactly sure. That's where you'd have to go visit with the math department, and hopefully they could explain all the mathematical problems down the road that this creates. Here's another problem. It limits the math that you can now use on your data. In other words, the statistics that you might want to calculate, you no longer can calculate. It's really difficult to use absolutes in computations. And again, sometimes I feel like I'm on a need-to-know basis, and this is something I don't really need to know. I need to know, and you need to know, that using absolutes is a bad idea, and it's a bad idea for these 2 reasons, but the nitty-gritty specifics, I never actually learned. Nobody ever taught me. So I don't know the answer to that, but if you're dying to know, then I'm sure somebody in the math department can help you out there. All right, so what do? The range is okay under a certain set of very limited circumstances, but the range is not used very often. Mean deviation and absolute mean deviation are not good at all.